It is basically this. You have a system defined by a certain transfer function g of s. As you know, there is an input u and there's an output y. Now we have a specific kind of input. This u is said to be u sine omega t, u0 sine omega t. So the input is a sinusoid. What is a sinusoid over time? It is something like this, a signal that goes up and down over the time, whose amplitude is u0, the magnitude of the signal is u0, and its frequency is omega, and frequency can be obtained from the period. Let's say that the period is t, so that the circular frequency, which is measured in radians per second, is omega. Okay. Now, this is a very specific, it might look like it is a very specific kind of input, but it is not. It is something very fundamental, and it is a very important tool in the analysis of systems. Now, we want to find what kind of output this system is going to have. Well, as we will be seeing, the output y of t, when the things settle down, that is in the steady state, eventually this thing is also going to be some kind of a sinusoid, okay, whose magnitude will be y0, let's say. And its frequency will again be omega. That is, if this is omega, y of t will be something like y0 sine omega t plus some phase angle. Okay. We have seen this in the vibrations class also. When you force a system with a sinusoid, the output will be a sinusoid of the same frequency with a phase shift. Okay, so so u of t is u0 sine omega t. Output is y0 sine omega t plus 5. Now, well, these quantities, u0 is the amplitude of the input amplitude. Y0 is the output amplitude, as you see. And phi, this phi thing is called the phase angle. And omega is the, as you know, is the frequency. Circular frequency or frequency. Now, we say that the steady state value of the signal, output signal, will be some y0 sine omega t plus a phase angle. Okay. And now this y0 has to be related to the system transfer function somehow. As a matter of fact, we will see that I will not prove this, but I will ask you to believe it for the time being. Now, g of s is the system transfer function. Okay. Now, g of, instead of s, if you substitute j omega instead of s, what we get is called the frequency response of a system. Now, this is a complex quantity, as you can guess. Now, why do we replace S by j omega? Well, you can see that in that video I have uploaded. Okay, I don't have too much time, but if you are interested, just watch that video to see why we replace S by j omega. So we replace S by, let's say, some quantity called j omega. J is, square root of -1. Omega is the frequency which we have been using, this one. Okay. For example, let's use g of s equals 1 over s plus 1. G of j omega will be, for example, 1 over j omega plus 1. Okay. If you want, you can play with this a little bit, like multiply it by minus j omega plus 1 in the numerator and denominator, and get, for example, what are you going to get? 1 minus j omega divided by omega squared plus 1, I suppose. So that it is 1 over omega squared plus 1 is the real part, minus j times omega over omega squared plus 1 is the imaginary part. So this is the real, and this is the imaginary part. Okay. So the frequency response of a system is basically a frequency-dependent complex number. Now, what does this have to do with our thing? Remember that we had u of t was u0 sine omega t, and y, the steady state value of t was y0 sine omega t plus phi. Okay. Now, what is this y? u0 is given. What is y0 and what is phi? That is what we want to find. Again, I will refer you to this video we have. It is shown that y0 is equal to the magnitude of the the frequency response times u0. Okay. Remember that g of j omega was a complex number. Okay. Its magnitude is real. So this is called the magnitude of the frequency response. You multiply that by the amplitude of the input, and to get the amplitude of the output. Okay. Moreover, the phase angle phi, which is again it will be a function of omega, this phi will be the well, it will be the, let me use this notation. Remember that in electricity course you had something like phasors, angle. Okay, so it is the angle of the frequency response. Now, this corresponds to the following. If you have a complex number with a real part and an imaginary part, this is your complex number. You can call it Z or whatever. It will have a real part and an imaginary part. Well, let's call it Z. Z will have a real part, let's say X, and an imaginary part, Y. So it will be X plus IY, okay? Or JY, maybe. We are using J's here. This magnitude of Z is going to be, as you can see from here, from Pythagoras, is X squared plus Y squared. Okay, the magnitude is the, well, if this is X and if this is Y, Z is the square root of X plus Y squared. And the angle, which I'll call theta, this theta angle is going to be, well, as you know, the tangent inverse of Y over X, for example. In our case, we have something very similar. We have real part of G and the imaginary part of G. So this is our transfer function G of, let's say, J omega. For a certain omega, this is the value. Let's call this angle phi. So the phi is equal to tangent inverse of imaginary part divided by the real part. And the magnitude of G of J omega will be the square root of real part of G of J square. Well, the equations look a little bit intimidating, but it is not really that difficult, okay? So this is called the magnitude of the transfer function, or magnitude of the frequency response, rather. And this is called the phase angle. And another thing is that just as you can represent this Z as, let's say, in the polar representation, Z times e to the j theta, rather. This is, remember, from 301. You can represent this thing as the transfer function G of J omega to be the magnitude G of J omega e to the J phi. Okay. Anyway, the important point being the following, though. I have to put these in boxes so that okay. The output magnitude is transfer function magnitude times the magnitude of the input, and the output phase is the angle of the frequency response, okay? Which can be found if you are given the system transfer function. Let me give you an example here. This is looks kind of difficult without an example. So let's have an example. Let's say that the g of s is a simple transfer function like 5 over s plus 2, let's say. And u of t is 7 sine 3t. So u0 is 7, omega is 3. So g of j3 is the frequency response. It is g of s evaluated at s equals j3, okay? Which is 5 divided by j3 plus 2.
Hocam, is there any reason that you are writing J3 instead of 3J?
It's the same thing.
Okay.
There is no reason actually. You can write 3j if you like. We will multiply it by the complex conjugate to separate the real and imaginary parts. So you will get 10 plus 10 minus 15j, let's say, divided by 13. We have 9 and 4, so 13. Or you can write this as 10 over 13 squared plus, something. Uh, 15 over 13 divided by 10 over 13. So it will be 15 over 10, right? Which will be the following: 1.387 into the. This is what I have written here. I'm not sure if this is j times 2, but this will be. This is in radians, by the way. Although it should be 1.5 according to this, but why is that?
Hocam, isn't it supposed to be tan inverse of 15 over 10?
I'm sorry?
Isn't it supposed to be tangent inverse in
Ah,
the...
there is a tangent inverse. That's right. That's right. Okay. There is a. That's why there is a tangent inverse here. Okay. Okay. As you can see, this is the magnitude. This is the g of j3 magnitude, and this is the phase angle, the phase of g of j3. Okay, in radians. So the output, if input is u is sine 3t, the output at steady state is going to be 7 is the input. Rather, I should say, let's multiply it by 1.387 times 7 is the amplitude. Sine 3t minus 0.982 radians. Okay, or you can write this as 9.709 sine, again 3t, minus, well, you can keep it as like this, or you can convert it to degrees if you like, 56.3 degrees. Okay. So if you look at it, the input, let's say it a little bit long, u of t and y of t, let's put it y of t in a different color. So u of t is a sinusoid of magnitude, what was it, 7. And this is u of t. I try to, draw it nicely, but it always gets. So this is u of t, let's suppose. The output will, our input magnitude is 7, as you see. You can find the frequency. The output magnitude is 9.7, so it will be a larger thing. Well, I will start this from a different kind of place. Let's say I will start it from here. The frequency has to be the same, but the amplitude is not the same. Okay, something like this. So this amplitude is 9.709. Let's see. Now, the reason I have started it from a point is in the beginning, there will be some transients which will die out, and then there will be the steady state response of the system, okay, which we are going to find, we are going to be finding. That's why I call it YSS here of T. So the steady state response of the system changes, and there is a phase shift, as you see. For example, between two peaks, between this peak and this peak, there is a difference, let's say, of Ty, let's say, and this phase angle is Ty over T times 2 pi in terms of the radius, and T being the period of this thing. How your signal shifts with respect to the input, okay? There will be a phase shift in the output. That's what this thing shows. So, as we see, the y steady state of t is therefore is equal to the general expression is g of j omega times u0. This is y0 sine omega t plus the phase angle phi of omega, let's call it, okay? So and the phase angle is as you know, is the angle of the complex frequency response. Note that both the magnitude of the frequency response and the phase angle g of j omega change as omega, the frequency omega changes, okay? So omega is the frequency of excitation. As this omega changes, both the amplitude and the phase change. So the frequency response, the so-called frequency response, G of j omega, this is an omega supposedly, omega of a system, let's say, is a complex, meaning that it has a real part and an imaginary part, function of frequency omega. Okay. Well, we can therefore find the response of systems to sinusoidal inputs. You are probably wondering why we are doing all this, but at this point, it is not so easy to, understand that. But as I have been telling you, this is fundamentally important in the analysis of systems. Frequency response is a tool that is very commonly used in system analysis. Therefore, it is very important. At first introduction, you probably don't get to appreciate that, but almost everything in the analysis of linear systems depends on the frequency response. So let me give you example, first order system, let's say. Let's say that the G of S is some gain over some time constant T S plus 1 is our transfer function. Okay. We want to find the frequency response of this system. Now, the frequency response is G of j omega. You replace S by j omega. That's easy. K over j omega T plus 1. Now, in this form, this is not very useful. You want to convert this to real and imaginary part form or to polar form. Polar form is the most useful, actually. So minus j omega t plus 1. J omega t plus 1. So what we get is that. Something like this, I suppose. We can write this as G of G of magnitude e to the minus, let's say, j pi of omega. Okay. Now, G of j omega, which is the amplitude or magnitude of the transfer function, is simply square root of the squares of these, which will be this is a long expression, but anyway. Squared here, right? Well, you collect the terms and cancel the things and so on, and eventually you will get k over plus omega. This is the amplitude of the transfer function. It's a function of omega, as you see, and the phase angle, the imaginary part divided by the real part, this part divided by this part. Now, nicely, this part divided by that part, and lots of things cancel, and you get, you know, minus k omega t divided by k. So it is minus tangent inverse of omega t. That is easy. Now, the frequency response, therefore, can be plotted in two plots. One is the amplitude plot, for example, g of j omega, the amplitude, versus the frequency omega. And the second plot will be the angle plot or the phase plot versus omega. So this is pi of omega. And the plots are like this. This starts from when omega is 0. You start from k, I suppose. You start from k. And then as omega goes to 0, it will go to 0. It will be some curve like this. Well, I can put it better. Something like this. And the phase angle, tangent inverse of omega, when omega is 0, it starts from tangent inverse of 0 is 0. So it starts from 0. And when omega goes to infinity, it goes to minus 90 degrees. So minus 90 degrees. It will be something like this. So we can represent the frequency response by two curves. One is the magnitude plot. The other is the phase angle plot. So we can plot different kinds of systems. Actually, in that video I have recorded, I have given you the example of a second order system too. A second order system also has a magnitude plot and a phase plot. Now, to represent the frequency response, the frequency response of a system, of systems, let's say, well, you have the following possibilities. One is called the Bode plots. These are the names of the people who have devised them. The second are the Nyquist plots. But we will be mostly looking at the Bode plot. I will very briefly look at Nyquist. But the Bode plots is important for us. Well, we don't evaluate the frequency response of these systems as we have done here. This is too long and too cumbersome. Okay, too you cannot do it. I could do it for a first order system, but you cannot do it for a fifth order system or something. So you have to devise some easier ways of representing systems. So the Bode plots and the Nyquist plots are represent, let's say, the frequency response of a system, which is g of j omega, in graphical form. And it is much better than having the equations. And they are very useful for quick hand plotting. Well, nowadays we don't use hand plotting anymore because we have computers, but still it's very important to be able to understand what you are doing. That is, you just by looking at the frequency response plot, you can understand what kind of system you are dealing with. And that requires some experience and requires some knowledge. And it is important to understand and interpret the results, although we don't really draw them by hand nowadays. And you have to draw it very briefly by hand. You have to know how to draw it by hand for the time being to be able to understand. So when we say the Bode plot, Bode is the name of the engineer. Actually, Bode plot is two, it's not just one plot. It's two plots, which is A is the magnitude, right? Magnitude of we are plotting the magnitude and the phase, as you see, not with respect to omega, but with respect to log of omega, the logarithmic. So these plots are logarithmic in the first place, okay? Why logarithmic? Basic reason is to represent lower frequencies, let's say, better. What does this mean? It means the following. If you have a normal plot, just a regular plot, you will have 0, 1, 2, let's say this will be 10. Well, where is 100? This will be 20, right? If you go to 100, well, you cannot really draw it here, but it becomes too hard to draw it. Whereas, if you use logarithmic, you can squeeze a lot of information. This is the linear plot, as you see. Whereas in the log plot, you have, well, you cannot have 0, but you can have 0.01, let's say. And you have 0.1, and you have 1, and you have 10, you have 100. All these differences are, so all the information from 0.1 to this will be 100. And you can even have 1,000, let's say, something like. So you can represent a lot of information in this plot. And as you see, the lower frequencies, like up to 1 or something, which has this much space here, can be given this much space. So it represents the lower frequencies in a much better scale. So the logarithmic plots are quite useful in some um, in many cases. Secondly, we also the magnitude is plotted in the logarithmic scale, and the phase is plotted in the linear scale. Therefore, actually, this is a, let me just put it here. This is a log-log plot in a way, the IA plot, and this is the second one is a semi-log plot, so that the y-axis is linear, whereas x-axis is logarithmic here in the phase angle. Why? Well, I guess we are out of time here. The next time I will start from this point, and we have too much information overload, I suppose. So let's stop here.